Hey everybody, welcome back. This is Mr. G again. Welcome back to the lecture series for Electric Circuits, Tech 101. Today what we're going to be talking about is series circuits. So in our previous lecture, what we covered was the basics of current and voltage with regard to a resistor, and we looked at Ohm's law. So we took a single resistor, tied it to a voltage supply, and then we looked at current flowing through that resistor. Now, that is a real simple concept. One resistor. Most circuits are not one resistor. They are a combination of 2, 3, and more resistors. So, what we're going to be looking at today is a circuit that contains more than one resistor. So we have a power supply and we have a resistor connected to another resistor connected to another resistor. When the resistors are connected end to end like this, so resistor 1, resistor 2, resistor 3. This is what's known as a series circuit. In other words, the resistors are connected in series. So what actually defines a series circuit? So if we took that exact same looking circuit and then I said R1, R2, R3, and then we have a voltage. Since we have a closed loop, so that means from the positive side of our battery all the way around to our negative side of the battery, there is a loop. So electrons can flow. So therefore, we can have current. So current is able to flow. So the current leaves the power supply and flows through the wires, gets this resistance, through this resistance, through this resistance, and then makes it all the way back to the power supply. If you notice, there is only one path in this particular case. There's only one path for current to go. So that must mean that the current, as it leaves the source, goes through this resistor, goes through this resistor, and goes through this resistor before it returns. So therefore, for resistors to be in series, they must share the same current. So that is the generic description of resistors in series. So resistors that are considered to be in series must share the same current. Now that doesn't mean they have to have the same current value. It means they must share the same current, and I'll explain that again in a moment. But the electrons, the exact electrons that are moving here, move through this one, move through this one, and move through this one. So they share the same current. As opposed to if I had a voltage supply and a resistor, and I said that that was 10 volts of DC, and the resistor was equal to 10 ohms. Ohm's law would say that 10 volts divided by 10 ohms gives us 1 amp of current. So that's resistor 1. And if I had another circuit right beside it, and that circuit had 100 volts and 100 ohms, Ohm's law would tell me 100 volts divided by 100 ohms would tell me that I have 1 amp of current flowing. 1 amp. 1 amp. These two are not in series. Even though they have the same value of current. So the current flowing through this resistor is 1 amp. The current flowing through this resistor is 1 amp. But it's not the same current. It's the same value of current, but it's not the same electrons. Okay? They are different. So in order for something to be considered to be in series, they must actually share the same current. So even though in this case the value of current is the same, it's not the same current. Here, the values will be the same, but also the electrons are the same. So that means the current that's flowing through one is exactly the same current that's flowing through here and here. So it has the same value and it has the same electrons. That's the difference. So it must share the same current, not just be the same value of current. It has to share the same current. So this resistor, and this resistor are said to be in series. So now that we have more than one resistor in a circuit, it changes the way we do our math a little bit when we solve for these circuits. So if I said that this was 10 volts, this was R1, this is R2, this is R3. These are in series because the current that would leave the supply, that current is shared by these three. So the current that flows down this wire goes through here, through here, through here, and returns. So if we looked at the current coming from the supply, so the total current in the circuit is equal to the current that is flowing through R1, which is equal to the current flowing through R2, which is equal to the current flowing through R3. All of the currents are exactly the same. Why? Because it is the same current. So I3 I3. We'll call this I2. And this is I1. So the current that's flowing through the whole circuit is identical to the current flowing through I1, or R1, sorry, the current flowing through R2, and the current flowing through R3. They are all the same current. So I total, which is what leaves the source, is the same as the current that is flowing through each of those resistors. So I just happen to have 3 resistors here, and I'm going to build this excuse me, exact circuit. So resistor 1, $33 kiloohms. Resistor 2, 18 kiloohms. Resistor 3, 10 kiloohms. So we have 3 resistors. We're going to hook them up into the circuit in a minute. So each one has its individual value. Each one limits the amount of current flowing in a circuit. If we want to figure out from the power supply's point of view what is the total number of resistance values, or what's the total number of resistance that we actually see. So if I was to put 2 dots here, and I looked from the power supply section, and I looked going that way at these 3 resistors, what total value of resistance would I see? In a series circuit, R total is actually equal to R1 plus R2 plus R3, etc., etc., etc. All of the resistances add up to be a total resistance against the total current flow. So in this example, I have 33 kiloohms plus 18 kiloohms plus 10 kiloohms gives me a total resistance of, we got 40, 51, 61. Kiloohms. 33, 43, 53, and 61. So 61 kiloohms. So our total resistance in this circuit is 61 kiloohms. Our total voltage applied is 10 volts. So therefore, what is the total current flowing in that circuit? So we have total current, according to our Ohm's law, current is equal to voltage divided by resistance. You'll notice that I'm using totals here. once we start combining resistors into circuits, we have different values. We have individuals and we have totals for the whole circuit. So when we're using or calculating totals, total is total divided by total. So in this particular case, that works out to be 10 volts divided by 61 kiloohms. So the total current that leaves the source in this particular case is 10 volts divided by 61 kiloohms. So the current is actually 0.164 milliamps. 0.164 milliamps, or 164 microamps, depending on how you like to say it. So the current that's leaving the source and flowing through this circuit is equal to 0.164 milliamps. So that's the totals. What about the individuals? So each individual has a resistance, has a current flowing through it, and a voltage drop. So let's take a look. So what is the current through R1? What is the current through R2? What is the current through R3? Well, according to our statement for determining a series circuit, all of the individual currents are exactly the same as the total because there's only one path, so they share the same current. So that means if I total is 0.164 milliamps, then all of these other values are exactly the same. Because it's the same current. All right. So we've got our I total. We have our individual currents. We have our R total. So now what we're going to do, just going to make some, move this up and make some space here. What about our individual voltages? So the voltage drop across R1, the voltage drop across R2, and the voltage drop across R3. Now Ohm's law tells us that voltage drop is current, so IR1 times R1, IR2 times R2, and IR3 times R3. So if we pulled out our calculator, we know that all the currents are the same. So we're going to say 0.164 exponent 3 to minus, so that is milliamps times 33K equals 5.4 volts. So the voltage drop across R1 is 5.4 volts. we've got 0.164 exponent 3 to the negative times 18K, 2.95 volts. 2.95 volts. And then the last one, 0.164 milli times 10K equals 1.64 volts. So I'm going to pull this sheet off here. So those are my individual voltage drops. So if I go back to my circuit, this was R1, this was R2, this was R3. Total voltage was 10 volts. And the current flowing, I total, and the total current was 0.164 milliamps. The resistance values were 33K, 18K, and 10 kiloohms. What does voltage R1 represent? Well, it represents a voltage drop, a potential difference from one side of the resistor to the other side of the resistor. 5.4 volts. VR2, what does it represent? It represents a voltage drop from one side of the resistor to the other. 2.95 volts. And the same thing here. 1.64 volts. Now, what is the value of voltage from here to here? That would be our 10 volts. So the drop from this point to this point, or the difference in potential from this point to this point, is 10 volts, right across the supply. If you look, you will find that 5.4 plus 2.95 plus 1.64 equals 10, or approximately, with rounding error. So let's take a look. 5.4 plus 2.95 plus 1.64. 10 volts. This is what's known as Kirchhoff's voltage law for a series circuit. Kirchhoff's voltage law. So Kirchhoff's voltage law states that all individual voltage drops in a series circuit must add up to the voltage applied. So again, Kirchhoff's voltage law for a series circuit states that all of the individual voltage drops must add up to the total. So that is Kirchhoff's voltage law. So Kirchhoff's voltage law for series circuits again states all of the individual voltage drops must add up to the total. In the textbook, you can find Kirchhoff's voltage law in chapter 5-6. So, looking at a series circuit, we have total values, so the total current. In a series circuit, that total current actually flows through each of these resistors. So they share the same current. Ohm's law tells us that if we take current and voltage, we can get resistance. Or if we take current and resistance, we can calculate our voltage. So the current flowing through this resistor multiplied by the value of resistance will give us the voltage potential from one side to the other side. Same thing here. If we know the current flowing through and multiply it by the resistance, what we would get is the voltage difference, or the potential, from one side of that resistor to the other. And the same thing over here. And then when we add all of the individual voltage drops, we add them up. According to Kirchhoff's voltage law for series circuits, they all add up to the total. So the individual voltage drops add up to the total voltage applied. So let's see if we can prove that. So I'm just going to take this circuit and move it up a little bit here. I'm going to build that circuit and we'll do these measurements. So let me see if where I have to be here. Let's try right about there. I can get everything on the camera. Good. So I've got these little resistors here. I'm going to place them in series. So we got the 33K, which is this one. $33K. Followed by the 18K. Followed by the 10K. So I'm going to take my supply at 10 volts. So from my power supply, we'll set this up for 10 volts. Yep. And we're going to apply the 10 volts to the circuit. So there we go. So the 10 volts is applied to the circuit. So now what I'm going to do is I'm going to prove these numbers. So I'm going to measure the voltage drop across that one resistor. So R1, voltage drop according to our calculations is 5.4 volts. So let's give it a whirl. 5.39. Then I am going to measure the next one. 2.95, 2.95. And then I'm going to measure the next one. 1.6. There you go, 1.6 volts. And the total, 10 volts. So now we'll prove our current. So I'm going to break the circuit like we did in the previous. I will set my meter to measure, and we'll try with the milliamps. I might have to go to the microamp scale, but let's give it a try. So now I'm going to put the meter in place so that the electrons leave the circuit, go up and get counted, and then return. So this should be somewhere around, okay, so let's see. There we go. 164 milliamps, 164 microamps, 164 microamps. So 0.164 milli is 164 microamps. So everything works out in our little circuit. So all of our measurements match our calculations almost perfect. Alright, so let's take another circuit example and solve. So let's say I put 12 volts here. This is a 1K resistor. This is going to be a 3K resistor. This is going to be a 4.7K resistor. And this is going to be a 2K resistor. So what we want to solve for is the voltage across R1, the voltage across R2, the voltage across R3, and the voltage across R4. So here's R1, R2, R3, and R4. What I'd like you to do at this minute is to stop the video and see if you can calculate the voltage drops across those four resistors. Then start the video again and see if your values match mine. Alright, welcome back. Let's see how you did. So what we're going to do is we are going to solve for this circuit. Alright, so the first thing that we need to do is we need to be able to, again, the final thing we're looking for is the voltage across each of those resistors. So what we need to do is calculate our total for the circuit. Use R total and V total to calculate for I total. So that's our first step. So R total is 1K plus 3K plus 4.7K plus 2K. So we put that into our trusty calculator. 1 plus 3 plus 4.7 plus 2 equals 10.7K. So 10.7 kiloohms. So our total resistance of the circuit is 10.7 kiloohms. We're now going to calculate I total. So remember, totals, we're going to use Ohm's law, but we're looking at a total, so we must use totals. The total voltage divided by the total resistance. That gives us the total current flowing in the circuit. So again, total current flowing in the circuit. So we have 12 volts divided by 10.7 kiloohms, and that's going to give us 12 volts divided by 10.7 kiloohms equals 1.12 milliamps. 1.12 milliamps. How you doing so far? So now that we know the total current, so that's the total current, and we know that that current flows through exactly the same for each of those resistors, because there's only one path. This is a series circuit. They all share the exact same current, and that current value is 1.12 milliamps. So if we were looking at the voltage across R1 is equal to the current through R1 times the value of resistance of R1. We know that the current through R1 is the same as I total. And we know what R1 is. So that works out to be 1.12 milliamps times 1K. And that works out to be 1.12 volts. 1.12 volts. VR2 is IR2 times R2. 1.12 milliamps times 3K. So bring out our calculator. 1.12 milliamps times 3K. 3.36 volts. 3.36 volts. There we go. 3.36 volts. VR3 is equal to IR3 plus, times R3 equals 1.12 milliamps times 4.7K equals, plug that into our calculator. So 1.12 milliamps times 4.7K, 5.26 volts. 5.26 volts. 5.26 volts. VR4 is equal to IR4 times R4, 0.12 milliamps, times 2K equals, and it's going to be twice that one, but let's just do it for fun. So 1.12 milliamps times 2.24 volts. 2.24 volts. 2.24 volts. All right. Did you get those values? I hope you did. The question becomes is, how do you know those values are right? And not just because I did them. How do you know that your values are right? Well, if you go back again to Kirchhoff's voltage law for a series circuit, it states that all of the individual voltages must add up to the total. So we have all of the individual voltages. Let's add them up. 1.12 plus 3.36 plus 5.26 plus 2.24 equals 11.98 volts. 11.98 volts. Our supply was 12 volts. So taking into account any kind of rounding error, those are the correct values for the voltage drops across those resistors in a series circuit. So again, VR1, that is the difference in potential from one side of the resistor to the other, 1.12 volts. This one here, 3.36 volts. This one here, 5.26 volts. And the last one, 2.24 volts. And when you add all of those drops up, they must add up to the total, according to Kirchhoff's voltage law for series circuits. So, what is a series circuit? When you have a combination of resistors in a circuit and they all share the same current, that is how you define a series circuit. So they share the same current. So chapter 5-1 all the way up pretty much to 5-7 is what we're covering. Principles of Electric Circuits, Floyd and Buckla, 10th edition. I hope this helps. Everybody stay safe. We'll see you again next time. Take care.